are often presented to us unsorted. Whether it's a budget for a month, frame data for a video game, or times in a race, these are rarely recorded in a perfectly sorted array. The insertion sort is one effective method for sorting a list of data from least value to greatest, and is invaluable, especially to data scientists who must process large amounts of data in limited amounts of time. On my screen here, I have what is a rendition in Java of the insertion sort. This top part here is simply initializing the array that we will be sorting. In this case, it is these values right here, 12, 11, 13, 5, and 6. The real bulk of the code and the core of the insertion sort, you'll notice that we have three variables initialized: I, j, and a variable called key. You'll notice that I, initialized in this for right here, does not actually iterate through the entire array. Since an array starts at index 0, I is only initialized at index 1. This is because for an insertion sort, we need to compare two values. The second value that we will compare is j, which is noted at I minus 1. If we were to take the first initialization of I would be at the second index, and j would be at the first index, thus comparing the first and second items of an array. This code right here is moving three things. It is moving I to the next value, j to the next value, and key to a certain value. Our key is placed in the values just to the left, of which we have not sorted yet. This last part of the code right here is simply printing out the array. While this may seem confusing, the core of the insertion sort is simply finding value in front of another value and comparing the two. If the value in front is greater than the value behind it, it stays in that place, our key moves on, our I moves on, and our j moves on. However, if the value in front is lesser than the value behind it, the two values switch. Our key stays the same, but our I and our j continue moving down the array list until that value is greater than or equal to the value behind it.
To better illustrate the concept of an insertion sort, I will use a more conventional example. Say you are a cashier, and the customer hands you back a handful of change in order to pay for their order. Here, this array of change is unsorted. However, with the insertion sort, you will be able to sort this. You'll see here that we have initialized a variable I. I starts at index 1, which, because of the zero-based indexing of Java, actually starts the second coin here. J was initialized to be I minus 1, and therefore starts 1 before I and at the first index of our array. The variable key here I have represented by this arrow. Key will keep track of where we have stopped sorting and where we need to go sort. So in this array, currently I have 1 quarter, 1 penny, 1 dime, $1 coin, 1 dime, 1 penny, 1 dime, a quarter, 1 penny, 1 dime, and a nickel. And we will sort this via the insertion sort by value of change. First, we compare the first two indexes of our array. You'll see I has initialized and started at 1, j has initialized and started at I minus 1, which is 0, and our key starts at our array I. So first I compare the quarter and the penny. Since a penny is worth less than a quarter, I will move the penny behind the quarter. And now we can see that at index 0 we have a penny, and at index 1 we have a quarter. Now our key progresses to the next value, our I progresses to the next value, and our j progresses to the next value. Here, our I is a dime, and our j is a quarter. Since a dime is worth less than a quarter, we switch the two values. Therefore, going from our quarter being at index 1 to index 2, and our dime being from index 2 to index 1. However, we are not done yet with this sort. We will see that j and I will both move back 1. And while our key stays the same, marking the spot where we stop sorting, we need to still compare our I and our j. Since a penny is worth less than a dime, we can see that this part has already been sorted. So now, we may move our key up to the next index, our I follows the key, and the j follows behind the I. We can see that up to the point of the index, I, everything has been sorted. Now, we see that we have a dollar coin. This is the coin worth most in all of the array list, and thus will end up last. So now we compare our I and our j. A dollar is worth more than a quarter, so we can move on our key, our I, and our j. Continuing this process, we see that a dime is worth less than the dollar coin, so we may switch these, move our I and j down. A dime is worth less than a quarter, so we may switch these, move our I and j down. Since a dime is less than or equal to this other dime right here, we may say that it's sorted and move up in our array. And the array sort continues as such. This array right here has 11 items and thus would have an index up to 10 based on the zero indexing system. Using this and moving the I, j, and key values, I will continue to sort through the array. Now we can see that we have gotten to the last index of our array, which is a nickel. You can see that before, what we did is we simply moved I to our key index and our j followed, and we compared I and j moving down until we got that they were equal or greater than. Finalizing the nickel, we can see that our nickel is greater than that dollar coin, so we will move the 2, move the 2, move the 2. Now we see that index I and j is a dime, I is still a nickel. So now we continue down the line again. And now we can see that there are no more indexes in our array to be sorted. All of the coins have been sorted in ascending order of value. Key, I, and j are now finished. They have done their job. So the insertion sort would be complete, and this array would be returned.